Good evening and welcome to the December edition of the Smart Grid Educational Series seminar, live here from the IBM Innovation Center in Foster City, California. We are privileged to have NIKSUN, the company that provides network monitoring and cybersecurity solutions for a variety of verticals, is here to talk about this field that is becoming very important in smart grid as the traffic that utilities have to handle is growing rapidly with all the new applications. So in smart grid, if we think of the paradigm shift that is occurring, and our speaker is going to talk a little bit more about it, what we're finding is that applications such as advanced metering infrastructure, demand response, electric vehicles, wide area monitoring, protection and control, distributed grid management, and many other applications that are now being implemented in a highly networked infrastructure are putting a lot of burden on the communication links. Technology is improving. High bandwidth networks are being made available more and more at more cost-effective prices. But when you combine the aspect of cybersecurity with this improvement in the networking technology, you're faced with quite a challenge. Because as the number of bits that you have to process go up, it becomes harder and harder to identify anomalous behavior successfully. You end up having a lot of false positives. So many systems for cybersecurity, such as firewalls and intrusion detection systems and other devices that you put, have some scalability issues when you start getting into the gigabit type speeds in identifying, with very high level of accuracy what is happening. Now you combine that technological hurdle with the changing threat situation. With highly networked infrastructure, you can have people from the public internet, you can have people within an organization, or you could have disgruntled employees taking advantage of this infrastructure, this highly networked infrastructure, to create new attack surfaces and compromise the infrastructure. We have learned from the Stuxnet virus that even physical isolation is not enough, that you have to have proper procedures in place for whitelisting of applications. You've got to make sure that the malware that can accidentally come on employees' computer systems is not plugged in to an infrastructure without proper screening. And that is what happened with Stuxnet, where employees who went on the public internet, got malware, which then, when it came and got connected to their secure systems, crossed the air gap and caused significant problems in that country. But that was not limited to that country, because the type of malware it didn't have a visa or a passport. It went everywhere where that particular vendor's systems were there. So the thing that we are learning from this is that we have to become more and more sophisticated in our approach to cybersecurity as these new threat vectors are exercising themselves on vulnerabilities that are known, as well as vulnerabilities that are not known. And it is that not known part that needs to be further analyzed. And one way of doing that is by studying the traffic, looking for anomalous behaviors, and doing correlation across the infrastructure, looking for what you call signature-less type attacks. The ones that are at such an early stage that you can't really identify them except when you start looking at the infrastructure in a systemic manner. When you look at the different layers, network layer, TCP layer, application layer, even into semantic and business process layers of the GWAC stack. And you correlate across multiple subdomains, and you look for patterns, and it's an adaptive learning process also, because as you get compromised, you learn from that experience, so the next time you're better able to see that anomalous behavior. This is not just a science, this is an art, because it combines computational capability with advanced mathematical concepts, and then a human mind that keeps adapting to a changing environment as these new threats occur. So we are very privileged. I'm giving you this background because I'm trying to motivate why it's important at this time and not 10 years ago or 20 years ago. Why is it important now to have this kind of capability in our hands? So what we have today is a presentation that will talk a little bit about the science and the art of identifying anomalous behaviors when you are monitoring pipes that can go up into the multi-gigabit type speeds. Where previously it was thought that you couldn't find something, this disruptive way of doing things helps you find some fruits that were previously unachievable. 5 or 10 years ago, the computational capacity wasn't there to do the kinds of things we are able to do. So we have to keep up with the pace with Moore's law, but then we also have to develop an understanding of all the different attributes of the electric sector, the infrastructure, that can allow us to get more information than we previously did by having this systemic view. So I would like to introduce now Shivank, who is from NIKSUN, NIKSUN, and he's going to talk a little bit about this field and then talk about some innovative solutions. So with that, welcome, Shivank.
Thanks, Erfan. So I kind of just wanted to give a quick overview of what I'll start with, and I guess I want to make this as interactive as possible. So feel free to ask questions. There'll obviously be a Q&A session at the end. And so my name is Shivank. I manage the basically I'm responsible for building the cybersecurity products at NIKSUN. And today, just wanted to talk about what are the big challenges that we see in smart grids from a cybersecurity perspective. So I'll talk about conventional power grids real quick. What is a smart grid? What are the objectives? What are some of the challenges that we see? What are the trends we're seeing in the security industry, which we're actually seeing in other sectors and may apply here as well. Some examples, including Stuxnet, a little bit of a small deep dive. What are the analysis trends? What is the industry doing to try to determine and catch these kind of attacks before they happen? And finally, a comprehensive cybersecurity strategy. And if you have the opportunity, a quick demo, and then we'll take questions. So conventional power grids, basically you have the power generation, you have transmission, distribution, and finally consumption. And they've traditionally been very isolated. They've had serial connections. They've really not had an IP or a radio frequency-based infrastructure. Whereas smart grids essentially take the electrical infrastructure that was available from power grids and combine it with the communications infrastructure with sensors, smart sensors, and information technology to sort of drive all these operations. So what does this mean? What is the difference between a traditional power system and a smart grid? If you look here, before the smart grid, it's a little difficult to see. There's the electrical infrastructure up at the top and the intelligence infrastructure below. And they used to be isolated. The communication channel did not use public networks. And with the smart grid, obviously this has been integrated. Devices, control, your SCADA networks, all the way down to your distribution channels. Everything is, all your devices are now essentially IP-based or radio frequency-based, WiMAX-based, etc. And hence, it has come in the public realm, and obviously people can access these devices remotely. So just to recap, I'm sure everyone here is familiar with the smart grid objectives. The biggest one being reliability. The energy industry is known for for reliability, but in cases of what we had back on the East Coast, we had the hurricane recently, and there was a lot of power outages. It took a lot of time to bring them back up. With reliability, the idea is you have automated real-time monitoring, and you have self-healing and self-activating equipment to essentially improve the availability of power at all times. Smart metering obviously is one of the big things. The AMI, the infrastructure. With smart meters, consumers and the utilities both have access to real-time information on how power is being used, and they can both tailor their needs accordingly, needs and pricing and so on and so forth. So it's basically driving towards a free market model of business operations. Going green is another big objective, so accommodation of alternate power sources, where power sources could come from, you could have alternate power generation mechanisms, so solar farms, wind farms, solar cell farms, etc. In fact, you could even have houses acting as sources of power in difficult times, if you will, or in times of need. Efficiency, optimized power generation, remote maintenance, basically balancing supply and demand real time, and security, which is improved monitoring and improved authentication and access control for, let's say, for users who want to access their information. So that said, I want to sort of talk about a little bit more in detail now about the cybersecurity challenges. What does all this mean from a cybersecurity perspective? So the biggest challenge which the utilities will face or are facing is the integration of renewable energy sources, integration of IT devices, diverse IT devices into a network. Basically, you have exposed all these units out on a public network. You have accounted for new sources of energy, and basically you have a two-way communication, so you have protocols being developed. And there's a lot more complexity which is coming in the picture because of this. And the number one driver for security in general is complexity. When you have more protocols, when you have more applications to decode, when you have certain established fundamentals, and you basically add to it, you are increasing the complexity of a system and introducing the possibility of loopholes. Then again, as I mentioned, the IT infrastructure is diverse. You have different utility companies with different IT infrastructures. You have, each one can have its own security foundations. And the other thing to note is that most of the assets are owned by private industry. So this means private industry has to work in conjunction with a lot of compliance rules that are coming from the public sector by NIST and CERT and so on. So there's a lot of different, high amount of diversity. There's not a common standards, and this introduces a unique set of challenges. For example, there are some smart meters which are found to lack proper authentication or encryption support. So I could spoof to a certain smart meter, pretending to be a control center or a utility. The other big challenge which we're seeing in utilities and across other sectors is big data. Especially, you have millions of households, your smart meters providing information. You have control centers. How do you correlate this information? How do you process it? How do you find what's important to you, right? And information processing, data mining. When you do have an incident, how do you mine the data quickly, right? So how do you find the needle in the haystack quickly and cost effectively? The good news is that this has been seen before in other sectors. we've seen an explosion of mobile devices in ISPs, and they're having the same problem. If you look at it, it's actually a very similar parallel. They're having, we have smart meters in utilities. They have mobile devices in ISPs and other networks, and there's been an explosion there as well in terms of, not only the quantity of mobile devices, but also the applications that run on them. It's highly diverse. Protecting systems. So the threat of unauthorized access to control systems. So your SCADA systems, for example, they're nothing but servers. They have vulnerabilities themselves. Or even if they're isolated, there may be a server which both the attacker and the SCADA system talk to. So you may know a unit which knows a unit which knows a SCADA system. So it's going to be connected in some way or the other. And one of the things we found is there's this claim that SCADA networks are isolated, but there's often, for convenience, there's often a backdoor entrance or something which people keep open for their maintenance work on an ongoing basis. So there's a threat of unauthorized access to control systems. And generally, this is the most important layer to protect, because once you compromise the first device within a grid, it's easier to propagate down because there's trust relationships between that unit and other units within the network. Protecting data integrity is important. You want to protect customer data, which is in transit all the time, and you want accurate recordings. You don't want malformed commands, etc. And you also want data which is stored to be preserved and not to be tampered in any way. The third thing is protecting privacy. This is kind of interesting. If I can get information on power usage patterns, I can tell who is at their home, for example, or who's not there right now. So that leads to physical security concerns if I can find out who's out on vacation. Protecting networks, which is especially important in the utility sector, because in other sectors it could mean a small revenue drop, which is a big deal, but in the utility sector it could mean lack of availability of power. So things like denial of service, which are essentially where you flood, where either one host tries to bring a system down by overwhelming it using some loophole, or multiple units, distributed units, try to bring down a single server. This is a very powerful attack in the utility sector, and it's actually not very hard to implement. So the threat to control systems. So control systems used to be exotic hardware and software back in the 90s, and today they are basic PCs and operating systems which rely on IP and basic internet access. This is a huge change in the infrastructure. Where they used to be isolated before and it was much harder to get into, and we saw that Stuxnet actually managed to bypass that. Today it's out there, it's out in the open for people to run scans and start doing other operations from a security standpoint. Malware is a threat like any other system, again, because it's standard servers. They are prone to malware written for them, and malware could include viruses, worms, trojans, or spyware. The impact could be corrupting data, or bringing down communications, or installing a rootkit which opens backdoors into these systems, or we have keystroke loggers. There's always the insider threat. People inside who are frustrated and who want to damage or disrupt a system, who may be trying to do things like privilege escalations. I may go on a unit and try to bump myself from a regular user up to a root or a super user. Hacking and activism. This is all over the news, and basically when you have an outsider who's interested in who's curious about breaking into a system, right, wants to know about how to break into a SCADA system and what's happening between, or maybe collect some information on utilities. That's one thread. The other one is activism. If I want to send a message to a company, or I want to send a message to a group of people, this is another way of doing it. Another method these days. Terrorism, which is more severe in the intent. It's either to disable the SCADA system or to disrupt monitoring and control capability. So you could basically take over the system and feed false values, or you could take over some internal unit within the grid and pass incorrect information back up or down. You could even physically damage the critical infrastructure system, and I will talk about one incident where this actually happened accidentally. So the new trend of state-sponsored attacks or advanced persistent threats is on the rise. So national defenses are not yet very useful in mitigation, and there's a general reliance in the security industry on logs. So you kind of try to determine what happens by looking at log information, but these things are so complex, they're new, they've not been seen before. They generally employ zero-day attacks, or they are so massive in scale that it's really not possible to look at log information and determine this. And the victim remains they have the responsibility for detection and mitigation. It's if a company is compromised, it is still their responsibility to find out what happened, basically perform forensics and make sure their infrastructure is strong enough to withstand such attacks in the future. The other concept is what we call dirty pond, which is when you know there's an attack happening, there could be other attackers in collusion. Basically, one case where we worked with a bank where the bank's infrastructure was compromised by a denial of service attack, but there were other attackers who were working in conjunction to basically clone the website of the bank for their phishing attacks. So there were two attacks happening in parallel, and this sort of complicates the whole investigation even further. Low-frequency scans and attack circumventing detection tools. A lot of security groups, in various sectors use flow information. There's a Cisco protocol called NetFlow, which gives you connection records, which kind of feeds it to your server, and then you can process it and report on how your networks are doing. This information is not very helpful these days because it averages out useful trends. If you have a spike in your network utilization, it actually averages it out over time. And lastly, physical security, which cannot be underestimated. Access to facilities. You don't want to give wrong people the access. You want to make sure this is audited, it's controlled. You don't want to expose physical ports, because if you do so, then software-based access doesn't really have much value, because you can bypass VPNs and other connections by directly connecting to the physical port.
Let us take a moment and just quickly
go through it too fast.
Check on the chat window to make sure people on the thing are all good. So is everyone on the call following the audio just fine? If you could just put in the chat window that you can hear the speaker okay. Anyone online? I just wanted to make sure that.
There's one.
Okay, hear you just fine, still fine, sound is good. Okay, very good. I didn't want to lose all of you online because our speaker does speak softly. I just want to make sure you guys are all on. And we will have Q&A at the end of his talk, and it gives him an opportunity to take a breath. Thank you.
Okay. Just a few examples of some incidents which have happened with I guess with smart grids or older power utility systems. So Stuxnet is something which Erfan already talked about. It's one of the most high-profile cases with utilities. It was obviously designed for from a spying perspective. It was a sophisticated worm attack which camouflaged 4 zero-day vulnerabilities, which is attacks which have never been seen before, and which were obviously not the result of. You cannot have a basic. Basically, it requires a lot of sophistication to develop a zero-day attack, because you have to reverse compile code. You have to look at, for example, how browsers and how operating systems work, and all the way down to very basic machine language, and kind of find out issues at that level. So it was a very sophisticated attack, and the SCADA system which was used in the Iranian the uranium enrichment process was compromised, was basically isolated, but there was a user who had an infected unit and brought the unit to the premises, and basically that's how the compromise took place. But what's interesting here is how targeted the attack was. So basically, the person who's working in the facilities, that information had to be provided, and the attackers knew who the person was, infected their laptop by whatever means, and kind of knew what the step-by-step process would be. And furthermore, the attack was isolated, so it could only target SCADA systems with a certain configuration. It wouldn't target any other server. It would only look for certain frequencies and very specific hardware configurations and target those. So it used multiple windows, penetrated and isolated network, strictly targeted systems with hardware configurations. It was definitely the work of a nation state. There's really no other way. I don't think any company is capable of investing this much effort, months and months into, something like estimated between 10 to 30 developers just to create 4 zero-day vulnerabilities and put it as part of, a package which can be exploited. Highly sophisticated attack. And there was another one which is very similar. There was Flame, which came out earlier this year, which actually borrowed 2 of the attacks used in Stuxnet, which is interesting because there is a repeat here, and that should trigger off certain things in terms of detection patterns, and I will get to that shortly. So Stuxnet, Flame, there's been a few other ones, lower profile ones, which have infected the industry. I'm just going to let you read this one, but this is from way back in '99. It really has nothing much to do with network security, but it's very interesting what can happen if someone puts bad code on, basically on your production network. And in this example, there's a company which had a practice of updating their development environment with directly with test code, and this happened with a utility company back in '99, led to a big explosion, loss of lives, there was a $45 million cost associated with it, just because someone was updating a production environment for utilities with code, and this was an isolated network at the time. So I think the point to think about is a lot of these are now exposed to external attackers. People have direct access to these units. So what changing certain attributes in a code can do. And later on, when there was further investigation performed, it says that although no evidence was found to suggest that an intrusion by an unauthorized or unknown user caused the computer slowdown, the lack of basic security features related to a SCADA system could allow such an intrusion in the future. So basically, they said it was very possible for an external user to compromise the system, even at the time. There was another example here where a smaller scale example where someone compromised a SCADA system using what we call scanners, vulnerability scanners. So essentially, you would look for vulnerabilities. You would just scan the network, the internet, looking for SCADA systems which come back with hits, right? And you might just bump on something. So this person actually did that. May have been a more targeted attack, and found a system, a Siemens semantic human-machine interface, which was accessible from the internet and was protected with a 3-character password, which is trivial to crack. So I think the list of examples goes on, but I kind of left it at 3. Here are some of the analysis trends, what the industry is doing what are the latest trends, I would say, in terms of identifying issues. DNS and URI-based analysis is very powerful. If basically whenever you have a user go to request a URL which is known to be malicious, a blacklisted URL, that should trigger an alert, and that should be taken very seriously. In DNS, there's another concept called DNS fluxing, which is your DNS records have a certain time after which they expire, and if this number is seen to be very low, is generally the sign of a malicious website, because they're changing their host name so frequently that you won't be able to catch this. So their records expire, and hence you're forced to go back to the primary DNS server, get a new copy of the DNS record, etc. So there are techniques around DNS which are highly effective. And just to recap, DNS is a protocol which is, all it does is it's a name service to an IP address mapping. That's all it does, because we cannot be expected to remember IP addresses. We assign host names, and we kind of just use that for further. So DNS is a protocol which has many hidden benefits for security. The second thing is there's state-sponsored polymorphic attack vectors. So basically, you don't use a single thing anymore to do attacks. Your attacks are a combination of multiple things. So you need correlation. You need a lot more than, let's say, signatures to be able to detect attacks in the wild. The third thing is finding focused attacks coming in multiple waves over weeks. So, actors are recycling the same botnets for different workloads. Basically, you have different botnets which are run by rootkits by different, the attack packages, if you will. And those attack packages are being recycled between different vendors in the black market. So you can sort of see similarities and derive that there's something incorrect happening there. So even when I just mentioned Stuxnet and Flame reused a couple of vulnerabilities from Stuxnet. So that should tell you something about how things are being recycled, even in this space. Abuse of cloud resources, which is obviously becoming a hot target as you have more and more infected pieces within the cloud. Long-term look-back capability, the idea that you can go back in time, and if you have access to all the data, rerun, let's say you have signatures, you want to do signatures retrospectively, right? Go back, you've recorded all the data, now you know there was an attack, so you write new signatures, go back in time, run it against your data, and find who else got infected. So retroactive detection, I've mentioned that with IDS. So IDS, the signature detection systems, which are very common in the security world, are becoming less useful in real time because of the false positive rate, but they're useful retroactively. And finally, antiviruses are becoming less useful in detection and mitigation. I'm not sure how many of you have actually, how many of your antivirus have actually found issues recently, right? I for one have not seen many. So difficulty with detection systems. There was an article in the ACM a while back about about the correlation between intrusion detection systems false positive rate and the perception of quality. How much trust can I have on my intrusion detection system because of the rate of false positives? There were few definitions. There was, for example, the true positive rate, false positive rate, and a user trust. A bunch of probabilities saying that if, what is the rate of alarms generated if there was an intrusion, given there's no intrusion, and the probability of an attack when an alarm actually gets generated. The thing to note here is, the false positive rate is extremely low, but even with small increases in the false positive rate, the trust level in that system drops significantly. And there was an article in InfoSecurity about federal networks which were attacked 15,000 times per day in 2010, something like 5.4 million hits in 2010. So how do you expect to mine that kind of information? So that said, kind of have an approach, at NIKSUN we've been sort of thinking about what are the important factors, what can we do to counter all these threats that we see in the industry, in utilities, other sectors. And the threats are very common actually in many respects. So the first thing is there's a concept of knowing the unknown. There's actually three types of information. There's the known. Basically, I know what I know. I know there are certain vulnerabilities which exist and I have signatures for them. There's the known unknown, in which I know there are certain things which are beyond me, and I cannot do anything about it at the time. For example, there's a 0-day vulnerability, but there's no patch available for it from the vendor. So I'm kind of helpless in that respect. I can do something about it by bringing my server offline or migrating it, but that's an expensive, time-consuming process. I have to find other ways to mitigate that. And then there's the unknown, which is I have no idea what's going on in my network. I don't know who's penetrated my network, what's happening, who's collecting information. So I think the focus has to be on this part, knowing the unknown, which is the most risky, because you don't want to find out, if there's something which you totally overlooked. So going beyond signatures, detecting anomalies within the network. The second is the concept of network discovery. So basically providing users the ability to go around in the network, get a bird's eye view of what's going on, and to be able to drill down and isolate areas of interest. So you can provide things like metadata, security metadata. If you use HTTP, if there's a lot of HTTP on your network, then user agent strings, HTTP query strings. There's a lot of other meaningful metadata, which for a security analyst will have a lot of value. A big thing is scalability because of all the big data that we see these days. A strategy which can be very effective here, which we've seen with ISPs, with who have remote offices and whatnot, and here with utilities where you have residential area networks, community networks, and finally you have regional networks, is to have a multi-tiered solution. You have smaller units for the smaller locations, and you kind of keep increasing that and percolate events and data upwards. So events can be going in real time to your top level tier, and data can be on demand. As I investigate events at my top tier, I can pull data relevant to it at this level. So scalability, you want different level of units. You want to aggregate at a top level. You want to deal with large volumes of data and events. You want to account for a very large number of remote sites. In this case, all your customer smart meters, all the grid units which make up the infrastructure. You want to be able to mine data and metadata of interest very quickly, right? When you're doing an investigation, you don't want to be frustrated trying to find a few packets for that application which actually caused this. You want to be able to get to that very quickly. In-depth forensics is very important because often you want to learn from your experiences. Attacks will keep happening. You do want to know what happened and prepare for it going forward. And it helps you also know the unknown part at the time, at least, and sort of discover what actually happened. It can be used for lawful purposes. You can actually take that as evidence against a certain perpetrator. And network-based forensics are especially powerful because when attackers compromise a unit, often what they do is remove any traces of what they actually did. So if they had a rootkit or something, they would delete the rootkit once they're done with their operations, close the backdoor, etc. But with network-based forensics, it's actually being captured by a quiet unit, a unit in non-promiscuous mode. So it would know, what files got transferred, what protocols were exchanged, what exactly the user got. So it's very powerful from that perspective. Deep packet inspection is a big name these days, which is essentially I want to capture all my packets, and I want to look at every single packet. I don't want to just look at the first few bytes where I can get all my TCP and IP and just a little bit of the application header. I actually want to parse the entire thing, and I want to find deviations from my expected protocol. So if I see a certain get string which is longer than what HTTP would normally see, then alert me on it. So these are deep packet inspectors. They're highly sophisticated in what they do. The other thing is obviously you want to thwart, attacks before they happen. You want to use IPS or preventive kind of systems to thwart, to basically thwart attacks. There are certain things which you know for sure are signs of someone trying to find out about your network. Things like port scans. There should be no legitimate case of someone. There are a few applications here and there, but you can make exceptions for them in your security scheme. But more or less, port scans, host scans, someone kind of scanning your network, gathering information, the very first step for an attack can be thwarted right there. You can basically cut off the attacker block that using a firewall rules or an IPS or something similar. So other anomalous behavior, you want to detect on it and act on it fast. You have destination alerts. Let's say you have certain countries that you've marked as hostile and you don't want traffic into those countries, so you act on them fast. Often you'll see bogus IPs which are used in attacks, blacklisted URLs which I already talked about. So when I go to a site which is malicious, that's a blacklisted URL. It should act on it quickly and fast. Reconstruct connections thoroughly. If you want to see what the attacker did, if you want to open up the web pages that some user went to get compromised, or an email that led to the compromise, you want to reconstruct that application which led to this whole event. This is a subsection of forensics, but it's very, very powerful. And in one click, essentially, you can get down to that incident which caused a certain event or a catastrophe in some cases. The other powerful aspect about reconstruction is you have raw packets, but you can actually extract files, other metadata, and then perform local forensics using malware analyzers and other sophisticated tools that are available only on the desktop and not at a network level. Fingerprint applications. So traditionally on the network, all applications are identified by port numbers. Your browser is talking to a server on port 80 most likely. It might be talking on port 8080 or 8888. Few variations here and there, but more or less this is the norm. But often what we're seeing is these days attacks are being carried, or data exfiltration, which is once you completed an attack and you're stealing information. It's actually happening. You're using a safe port like port 80, but you're extracting some other information on it. So a very powerful suggestion to thwart this is to fingerprint applications. So as you're seeing each connection on the wire, you actually want to say, oh, I think this is HTTP, or I think this is SSH, or some other connection, or some other protocol. And the rest of the product can probably use that information, rather than rely on just heuristics like port numbers. Alerting on content. This is, I think, a very unique approach. Traditionally, security relies on packet-based signatures. Like IDSs look for signatures within packets, a certain combination of strings, characters, something like that. But and anomalies, which I defined before, look for traffic patterns. Like a botnet will have a low number of bytes over a long connection. That's a typical behavior of a botnet. So you have different patterns depicting different kinds of attacks and behavior. With content, you can actually detect files as they're going over the network in real time. So which is a very cool thing, because let's say you have known rootkits, or you have known executables which are malicious, or you have Windows files which you shouldn't be seeing transmitted over your network. Now you can actually detect these on the wire, report on them, high level of accuracy, and very powerful in forensics and real-time detection. Retrospective IDS is something I already talked about. If you're a large, large packet capture device, you have all the packets. Now, let's say you found out an incident happened. Now you can go back and you can write some new signatures, and you can replay all the packets and see who else got infected in your network, where else you saw the signature come up. Very powerful approach. Replay traffic to other devices. This is useful if you want to test firewall rules. So again, if you've recorded all packets, you have third-party systems to which you can feed the recorded information and test your firewall rules and so on. Architecture needs for scalability. So some of the things which we've done at NIKSUN, and from an engineering standpoint, these are kind of interesting. There's a concept called multi-timescale analysis, which is I want to be able to drill down on data from and kind of make it more and more granular. So I might start with looking at 1 day time period, or maybe a 1 month time period, and I notice there's a spike, and I keep drilling down on it until I get very fine-grained second-level information on what actually happened. So that's one of the technologies which build the foundation at NIKSUN, and it's something which is extremely powerful in terms of doing performance or security analytics. Stream-to-disk technology is another aspect, which is where you write data at very high rates, you stream them to disk, And while you're streaming them to disk, you actually compute statistics on the fly. You extract metadata, you calculate averages, you have different kinds of buckets where you store information so you can retrieve it later quickly. The third thing which we think is very powerful is server-side rendering, which is you don't always need to have client-side executables to perform forensics. You should be able to do this on the server side. If I want to find packets which are malicious, I have a certain string that I want to search. I want the server to do it because it's a lot more powerful than my client. And besides, I don't need to download gigabits of data and then try to run it because my laptop probably cannot handle that in terms of memory. So server-side rendering is very powerful. Web-based access is, allows multiple users to access from any unit. Security meets performance. A lot of performance metrics can be used in security, and we've done this with something called anomaly alarms, which is traffic patterns, as I mentioned before, for botnets, or even host scans technically are sort of a performance metric. Product-wide pivoting means that at any part of the product, I want to give the user access to all the tools which exist within my product. So, for example, if I have a GeoIP detector, which means that, let's say I have a spike in a graph and I want to find out what GeoIP locations, what geographic countries resulted in that spike, because that may be of interest to me from a national security standpoint. We have that, available, and that's easy to use. Easy third-party integration. You have things called CMs, which are correlation engines. You have different IDSs which feed into CMs and do the correlation. A big example is ArcSight, which is a big player in this, and there should be an easy way to actually integrate with third-party systems. And we've done this from a technology standpoint. We've done this using something called web services, Java Web Services, which is essentially it's an XML. You make a call, you make a URL request, and you get an XML of data back, and you process that data. It's an easy way to integrate with third-party systems. Strong access control policies. Obviously, the product that you're designing should have access control policies. And finally, it should be highly customizable, so you can allow different users to customize their dashboards. And you don't want, you don't want to keep, and you don't want to share the dashboards until the user explicitly permits sharing them. So just some references. Okay, I don't know how I'm doing on time, but
oh, you're fine.
So I thought I'll quickly just maybe first I'll just take a pause. I don't know if anyone has questions or if I can jump into the demo, please.
Can you expand on the notion of DNS fluxing?
Oh, DNS fluxing? So generally DNS records have a minimum value of I think an hour. So DNS records, so let's say I go to yahoo.com and I have my internal DNS server in my local network. So that talks to yahoo.com. It gets a record from there and it says that here are the IPs for yahoo.com, and it remembers that for 1 hour. So any user who's going to Yahoo for the next hour will just use this cache that my local server had. But in cases of botnets, or even in case of WikiLeaks and things like that, the host name was changing very frequently, right? So so basically they were forcing the server to go back and get the new record, so you can find out what the so not the host name, the IP address was changing very frequently, which means that basically you're forced to go back to a DNS server, get the new record, and get the new IP address, because they're changing servers. Because WikiLeaks was, it kept being blocked by ISPs here. So the way they mitigated is they had this policy where you load DNS TTL records, and the DNS records expire in your local cache. So you're forced to go back to the external server and to the root servers, and they give you a new record with the new IP address. So that's how they kept migrating servers. This is also a common thing for a lot of botnets and other malicious blacklisted DNS-based activity.
So in order to monitor for security purposes, it sounds to me like you would have to monitor continuously, which means that the amount of data you will be collecting or capturing would be just humongous.
The amount of data you're capturing is going to be humongous. There has to be ways to kind of extract information of interest, and I can walk through one approach when I do the demo, and there has to be dashboards which are customizable for a certain environment. For example, different sectors have different threats. In the banking sector, it could be it could be denial of service, it could be cross-site scripting. These are common things seen in the banking sector. So you could create dashboards for only these kind of issues, and the user could just be monitoring this from time to time. So that's how you filter out from a lot of events. That's how you get this information. You could turn off certain ones which are noisy, and this is the fine-tuning process. Then obviously you have anomaly alerts which go a lot beyond signatures, because signatures for a large amount of data, too many false positives. So you want to go to things like anomaly alerts which have a much higher rate of accuracy, which are based on traffic patterns and which are based on protocol patterns. If, for example, if I have a large DNS packet, that should trigger off something, because I may be exfiltrating data in that DNS packet. I could be sending something off. So if I see a lot of these large DNS packets, that should send off some signals, and that's a very good chance that something's happening there, as opposed to IDS signatures which may result in false positives. So I think it has to be a holistic solution. You have to look at new technologies like anomalies and content-based detection, and use things like IDS for more retrospective analysis. A combination of this will lead to a much more effective solution, I think.
Questions?
Yeah.
Can you speak up?
Yeah, most of your discussion is centered around SCADA systems and everything. I worked in the industry for quite a while in both oil and pipeline thing, and most of them are actually private, networks, and in conjunction with IP and everything, that's in parallel. I mean, how many of them have you seen in only IP?
Yeah, repeat the question and then answer it.
Okay, so if I understood your question correctly, you're saying a lot of the SCADA networks that you're seeing are private networks. They weren't really exposed publicly.
Correct.
So I think the trend is what we're trying to address here, more than where we are currently. I think currently it's still quite isolated. But the trend is to move towards open networks, where you have public networks and private infrastructure, collude. And what this is more of a forecasting exercise at this point, where we foresee that when you actually come to that stage, a lot of these systems which were once isolated will be exposed. So at this point, I think we're still migrating. I think it's, like you said, we're not fully there. But once we do, then we will run into a lot of these issues seen in other sectors.
Yeah, and also the advent of Stuxnet, the use case of Stuxnet, if you look at it, crossed that air gap. So all the isolation in the world is not going to be enough. What we're seeing is that there is a people, there's a process, and there's a technology that all needs to come together. And so we learned that there were some processes that were missing. Now, in the case of the Iranian situation, the people who created it wanted that delay to occur, and it occurred. But let's talk about in the electric sector in the United States. If you are delivering electricity to a segment of the population that has no other alternative to receiving that power, and something happened to the SCADA system that made the availability of electricity intermittent, then the implications, not just the financial, but life. And we saw the example of the pipeline and how the SCADA got compromised that led to the death of those young people. So we could see this over and over again. So it's not just about the SCADA system being connected to a public internet or having some kind of a external connection. We're seeing increasingly that new threat vectors are being created that can cross the air gap. Simple memory stick, not doing a proper audit of a laptop of an employee that may come into an administrative network. You know, they have to check for every file since the last time the laptop was on. How many organizations are actually doing that? So there are these gaps, and so it's not as futuristic, actually.
We're getting there. In fact, on recollection, in my last company I was consulting, we were doing an audit for a large northwestern energy firm, and we found access. They were using, it was not a SCADA system, but I would say it's a very close approximation using some mainframes. And mainframes are prohibited from accessing, basically going out anywhere. There has to be no communication. But we did find a case where there was an intentional backdoor created to the mainframe system for convenience. Essentially, convenience is what always compromises security, and vice versa. They just don't get along. So we did see that, and we did raise that as a questionable issue in the audit. And this was at a very large firm. So the trend is there. It's not caught up as much as other sectors, but it's getting there. As we migrate, it's definitely becoming more and more visible.
Let us see online if there are any questions before we get into the demo.
Sure.
So if I can just bring the chat part down. Okay, so the question was, can we see the references again for a moment? I'll be sending out this document in PDF, and it'll be put up on a Dropbox. So you'll have access to all of these links. But if you want to see it right away for some reason, please go ahead and put a note, and we can go back to that slide. This was a note from Greg. Later we'll be fine. Okay, any other questions online? This would be a good opportunity, because then we're going to go into a demo, and then we'll come back for some follow-up questions. Any questions online? Okay, so if there are no questions online, then we'll go ahead and start with the demo.
More questions here, though.
Are there? Oh, more questions here. Go ahead.
You mentioned that if some employee comes in and brings it, jumps the air gap. I mean, one way is obviously to monitor all these things. But what if this particular user has specific permissions, and that permissions could lead to, let's say, major consequences? Are there protections specifically to prevent that, like multiple confirmation? I don't know.
There's a similar approach we've seen. I'll repeat the question. So the question is about insider threats. If there's someone with high level of access, what can be done to sort of prevent them from doing something malicious or catastrophic? Well, one of the things is, again, in my last experience, when we would go to companies and we would kind of help them develop a security strategy, we would identify, exactly who needs to have access to what. That's the most important thing. That is a hierarchical thing. Someone at the top decides what infrastructure is there. What we did do in one case is there's something called identity management systems, which essentially have a concept of workflows. So if I want to get access to a certain site, or if I want to do a certain operation, I have to go by a workflow each time. So there's no exception. It sends an email to someone who is, maybe my boss, and then he approves it, and then that's how we get access. So critical resources, I think, should have workflows associated with them. You could have 2 or 3 people in the hierarchy out of which maybe 1 or 2 needs to approve it, something like that. So the security structure can be defined, can be designed based on how large the organization is, what really the needs are. But I would say that's probably the best way to counter internal threats.
One of the things in cybersecurity in the new paradigm is that the default setting is that you don't trust anyone.
Yes, zero trust. That's the new norm.
You don't trust anyone, because trust in itself is a vulnerability.
Because once you compromise a system, then all the systems that there were trust relationships with are compromised, essentially.
So what you find out, and there's an adaptive learning process in an organization, that there are some things that are kosher behaviors, and some things are not kosher behaviors based on your job responsibility. So one of these things that we learned from the Sarbanes-Oxley, the reason why that legislation occurred is that people went beyond their job responsibilities and started doctoring things because they had more information than they were supposed to have. So the CFO, the CEO, the CIO, they all have their job responsibilities, and based on that, they should be privy to certain information. When it was a free-for-all, they could collude, and they could create new numbers for an organization, and that caused a lot of problems. So the lesson to be learned from Sarbanes-Oxley is the best security is where it's on a need-to-know basis. Now, if you have a certain job responsibility and you're sitting there doctoring applications, there needs to be something that's neutral, that's watching and just flagging it. It doesn't mean that immediately prosecution has to occur, but there has to be a process by which those anomalies are detected and taken to another party. Now, the probability, there's still a probability that they could all be colluding, and it's like a coordinated attack with like an industrial espionage ring that has multiple W-2 forms, and there are a bunch of employees, in the entire supply chain, but that likelihood is a lot lower. So by putting these added layers of observation, and by the way, security systems also need security, because
a lot of
people, hackers, can compromise the security system.
Yeah.
So there has to be something that's watching. So it's almost like, the communist Russia, where you had one level of security and then you had another level of security watching that security. So you may see organizations that have a sophisticated security architecture layering it like that. But at the end of the day, if you want to remain as a productive enterprise, there are certain things that you do and do regularly, and there are very clear job descriptions, and there is an authentication and authorization scheme through LDAP and other tools. So when you start doing stuff outside of what has been given as your privilege simply because you have some administrative right or something, that's still not good enough. You will be flagged, and there will be things done to, it could be career limiting. So I think that if you keep that mindset of being a little skeptical, and that's why people from the Northeast will do better in cybersecurity, because generally they're more skeptical. It's the weather or something. So they do better in cybersecurity because the default setting is, I don't trust you. So that way it will work. And then the challenge, by the way, with this, as Shivank showed, that the more detail you go into, and the faster the change is occurring in an environment, the harder it is to find that needle in the haystack. So that's why we cannot just do it on brute computational capacity alone. We have to develop an art. It's not just a science. And this is what Shivank has been showing, that step by step, when you address all of those issues that he showed as cybersecurity threats, and then he showed a way in which you have to deal with information coming to you. And you don't just throw it all in a bin and say, okay, now I'm going to just find it in the petabytes of data. This whole concept of metadata, labeling things, the queue theory almost, like as data is coming, you process it, like
extract interesting information,
extract information, and then have layered information so that you take the higher level and then it quickly triggers to more detailed information. But you don't have to look at the detailed information 24/7. So without further delay, let's start the demo. So kind of motivate us, tell us a little bit about what you're going to do before you do it, and then tell us what you showed us.
Sure. To be honest, this is a free form.
Okay.
This is a free form thing. It's nothing prepared.
Not a problem.
But what I do want to do is kind of go back to the PowerPoint. I've talked about some concepts like multi-time scale indexing, some technologies. I want to show what it looks like in a product form, and how it can be used to solve.
So let me check with the folks online if they can see this sign-in thing. Let me just get a confirmation from anyone online that you can see this little window with sign-in, username. Can you see that? Because we've gone from...
Yes.
Okay, very good. I just wanted to make sure, because we went from one schema to another. See, I don't trust anything. This is how it is. All right, thank you.
Just logging into the system. So basically, just to explain the setup, this is what we call an enterprise system. It's a demo unit. It's talking to a bunch of smaller appliances, and I'm just going to go in the central management location within this unit, and from there I'm going to go down to the actual small appliance itself, and talk about some of the technologies, see what they look like in a product format, and see how they can help with security, forensics, and investigations. So there's a couple of, within this enterprise system, there's a couple of appliances registered. I'm picking one of them, which is the security solution, and going there. So it's using single sign-on. There's a communication established between these two using that. So I want to start off talking about one of the key things which I think is very valuable, which is where performance industry meets security. So this is what we call the analysis tab, which gives you an idea about what's happening on the network, and you can see your top applications, you can see network traffic levels, and you can do things like, who are my top talkers, what's busy, and GeoIP information. What countries are talking to what other countries, based on what I'm monitoring. So,
how did you decide where it's going to, which country?
So IP ranges. So we have a infrastructure in the backend which maps IP ranges to country codes and countries. So it dynamically pulls it from there. And one of the things which we allow is to, if you have an organization which is very widespread, for example, let's say a department with embassies across the world, or a foreign company with many branches across the world, many development centers. So you don't want those IPs to be represented by those branches. So we allow the ability to basically map like your own country codes or your own codes to those IPs which correspond to your company. So they pop up everywhere in the product, and rather than think of just countries, now you have a granular level company-wide infrastructure which you can look into.
So in fact, you're hiding the country code?
Yes. In fact, what it does is, so let's say my let's say my IP range of US is, and I have 6-7 branches, and I have slots of IP addresses, external facing IP addresses within them. So I can actually take those IP addresses and splice the US GeoIP range to mark these as, this is my West Coast San Francisco office, this is my LA office, and so on and so forth. So the US GeoIP space is now split up into these smaller regional offices, and the rest remains obviously US. So when it pops up on your screen, you can see exactly which office it is, or so on and so forth. So let me see if I can perform some operations here. So essentially what it's doing is calculating application protocol detail, bitrate information, where to where from, right? So what we see here is, so what you see here are your protocols at the V-link layer, and I can obviously perform my analysis at different layers. And you're seeing other interesting information, such as what my bitrate look like for this traffic, what are my top countries that are talking here, and who are my top talkers on the network, what's busy, and so on. So the idea is you have a bird's eye view of your traffic. Now you can start your investigations from here, right? So you don't need to be mining million events or other things. You have a network-wide traffic, and I mentioned something called multi-time scale analysis. If you look at this plot, it's averaged over a large time period because this is a static data set, which means it's a pre-recorded data set of network packets, and it spans many years. It goes from 2003 to 2010. Small packets from here and there were picked up and clubbed to create this. Now, I want the ability to drill on any part. So I should be able to drill on this, for example, and update my view. So what this does is updates all the parts for that information that I drill down on. Now let's say I was interested in this small point here, right? And I don't know if I have that granularity in this. I guess I don't. So let me show you something else. So basically, the other thing I just wanted to, I'll get back to this why the zoom functionality is not working. Okay, I guess I don't have stats for that. But the other thing I could do is, you see this peak point here? I can perform other operations, like I can see the packets for this point. So at any point of my investigation, in fact, there are only 2 data points here. Maybe that's why it's not averaging. So at any point of the network, I can go to packets, or I can do things like IP host pairs for this point. So let me show you real quick. So for that point in time, here are all the host pairs I saw. Here are the packets and bytes that were consumed. So I can see that this IP address talked to this one, and so on and so forth. I can then, for example, view packets for anyone which I find interesting. So starting from a point in a graph, I can quickly go around to the packets, and let's try out a quick example here. Let's see this one, and say packet viewer.
Question.
Yeah.
Is the monitoring being done at the network level, or server level, or router level?
The monitoring, so as the packets are written to disk at the server, so the server is capturing network data, obviously, as it's going by. And as it's writing the data to disk, it's computing statistics on them. And the statistics is what you're seeing here. So it is the server capturing network data and generating metadata and other information on it, which you can then drill down on and perform further.
So the server, are you referring to the customer server or your server?
This is the this is on our server.
So basically, you're watching me.
Yes. Yes. Okay. Let me explain the physical positioning of this network. I know where you're going. So these kind of units, and this is a large packet capture device, right? It's basically a non-promiscuous mode, which means it's tapped into the network. It's listening quietly. No one knows about it. There's essentially no way to tell. Obviously, it's an IP device, so you can't tell. But it's no other devices are aware that this is there. And the idea is it's monitoring all the packets that flow in the wire. It's recording them to disk. And while it's recording to disk, it is calculating statistics on them for each packet and for an aggregation of all packets.
For a given server?
For your entire network.
Okay.
For your entire network, yes, yes.
Yeah, so if you go back maybe about 10, 15 years, and if you recall Armon, they used to have remote monitoring. And remember how we used to have segments, Ethernet segments, and you'd put this thing called, and you'd do what's called a fast packet capture. So every packet that was going by, what you do is if you have fiber, you put a fiber tap. So that's why you don't need an IP address on the link.
Yeah.
There may be an administrative IP address on the back side of the machine that an administrator will have control, for doing telnet or going through web services and going into it from that side. But from the pipe side, there is nothing, because all that it's doing is it's copying the packets as they're going by. So there is no intrusion whatsoever. It's not like it's stopping the flow and then putting it back. So these types of taps exist, and a lot of intrusion detection systems work like that. The key thing to understand here is that there are many technologies out there that are taking data from pipes and putting them into flat ASCII files. The problem with the flat ASCII file is who's going to sit there and go through reams and reams of data as a human being looking for that anomaly? So by massaging the data as it's coming and sorting it and labeling it and creating what as he's showing, a hierarchy of data with interrelationships, you can turn that data into actionable intelligence. That's the key value. Otherwise, packet copying has been going on for years.
Yeah. And just to add to that also, strategically where this is positioned in a network is you can have it, let's say, in your DMZ, which is where outside your firewall, your internal firewall. But so when I connect to yahoo.com, again, or google.com, their servers are located in their web servers are located in what's called a DMZ, demilitarized zone, which is not as safe as the internal network, but it's accessible. So depending on the posture of your security network, what you want to monitor. If you wanted to monitor the DMZ, then you would put a unit like this in that location, or you would put it before the firewall if you wanted to see what traffic was actually leaving the network. So you would monitor all your servers or all your users. So it's kind of a strategic decision whether you want to monitor a certain set of servers like your server farm, or if you want to watch what your users are doing. And you can tap in exactly there. Or you can have a Cisco device using a span port just channel traffic from certain VLANs or certain networks into this device. So you can pick what you want on the network and monitor that.
Yeah, for smart grids, you could have lots of smaller units distributed out at the plant,
exactly,
the aggregation point, and then you could aggregate all the data together in a
exactly. Yeah.
Can you repeat the point?
Yeah. So just to repeat Mike's point, so you can have smaller units which are distributed across in the smart grid. They're distributed across all the utilities, most granular location. Like in telecom industry, you have remote offices, so the equivalent is a residential area network or maybe a community network. You have small devices there, and they're collecting information, they're finding out what's interesting, and they're piping this over to large devices which sit at regional levels. So that could be the multi-tiered solution. Did I capture your point?
But they're piping only the metadata back, right?
But they're piping the metadata back, right? Obviously, the data is too huge to pipe back. So they're doing the intelligence. They have the same intelligence which the larger ones have. It's actually the same exact software, if you will, running on both. It's just different scale. And the other one may do a few other operations on top, obviously, but the intelligence of mining the metadata and of mining the events is similar.
Yeah, so the beauty is you can have one aggregation unit at a central office point, and you can see your entire network, and you can mine to each of those data connection units from a central point very quickly by going through the metadata and the multiple layers of data. Right. So it's a very powerful way of looking at and covering security for your entire network.
Yeah. So, I mean, as a contribution to the industry, because the focus of this educational series is to understand what the disruptive aspect of it is. That's the key. Well, that's the learning here. And that learning is that, A, all data, unlike the Constitution of the United States, is not created equal. Some data is more important than other data. However, there needs to be access to data at any granular level if needed. So in cybersecurity, we have confidentiality, which is created through authentication, encryption, things like that. We have integrity, so when we do checksums and things like that, we get integrity. We have availability, which is what percentage of the time is the application available to the users. But then there's accountability. Accountability requires forensics. This gives you that granular detail. Notice when you have pairs of IP addresses talking at designated times which are documented, you can take this to a court of law, and you can show that this individual was talking to this individual during this period of, and it holds, it sticks. It's like those digital signature, like when they do keystrokes of a hacker and they're recording it and it's digitally signed, that can be introduced in a court of law. So accountability is going to become key because there's a financial liability associated with accountability. It has financial implications. And having tools that allow you to go down and yet keep at the high level and have that eagle view is very important. It doesn't matter whether it's NIKSUN or some other company's product. The main thing to understand is the hierarchical aspect of data and the ability to quickly see an anomaly and be able to drill down quickly and use that information to protect your business.
But how useful is that in an encrypted network where the payload is encrypted and you only see the source and destination address?
So we have a, well, one of the things you can do in an encrypted network, there's two things of interest. So one is where you own the keys and one is where you don't, where you own the servers. Where you own the key, there's something which I call content level detection. And in the content level detection, anything going to your server can essentially be looked into because you have the master key. Now, but if you're thinking of connections which are leaving the network, then there's what's important there is you have to define your assets which would never be making a connection outgoing from your encrypted server, from your server. So, for example, I have a server which is valuable to me, and I do not want to see a connection, encrypted connection, originating from there, right? So you could create anomalies like that, basically tripwires on your network, to alert on certain activity like that. You should never be seeing any exfiltration happen over an encrypted channel, and you can look at patterns to detect that.
Yeah. I think all the smart grid's going to be encrypted, so I'm just really wondering what the value of this is.
Yeah. Well, you could forge a certificate. That's always there, because if you're posing as a utility, you could, as a control center, or basically where a user is expected to talk to you, you can forge a certificate, and if the user doesn't know enough about validating certificates, you could pretend to be the server they're talking to. So you could do a man in the middle by forging, by creating a self-signed certificate. So there's many different ways of kind of breaking the model.
Also, you're right about that the exposed parts will be seen as exposed, the IP addresses of source and destination. So you'll know pairs of conversation. You may not know what's going on in the conversation till a later time when you need to know that information, because when he's copying the packets, he's copying the encrypted data. So it would require a key at some time. So if you wanted to drill down because you realize that this pair that is working together should not be working, that becomes the anomalies. But you don't need to know the raw data at that instant of time. If later you want to go through a prosecution process, then you can subpoena for those keys and open them up. So you're right that encrypted data will not help you get to that granular level in real time. But it can at least, by monitoring it like this, you will know kosher pairs and unkosher pairs of IP addresses.
I guess you can find backdoors or left open and things like that. People are penetrating ports left open.
Certainly.
Yes.
Certainly.
Yes. So whatever is exposed will be valuable in real time. Whatever is not exposed can be valuable in a court of law.
Yeah. And you can monitor probes, I guess.
So we're running a little short on time. We have about 7 minutes. So if you can conclude your demo and then quickly give a round of Q&A so that because there are people on the East Coast and it's getting late for them.
Sure. Okay, so basically what I just wanted to show is some of the technologies here. This is a small static data set, so I'm not able to zoom in. But the idea is to be able to pivot from any point here, any graph, anywhere in the product, anything I find interesting. I have a bunch of tools at my disposal. Show me all the hosts, show me packets, show me any other information which is important from a security standpoint, or reconstruct the application, which I just wanted to show real quick. Reconstruction is essentially what it looked like to the original attacker. Extract the files from the raw packets, show me the web pages, and so on and so forth. So I'll pick the same data set just as a proof of concept. Application reconstruction again is looking at the raw packets and reconstructing the application as it looked like to the attacker or to the user. Trying to look for a web page here. So there are some emails which went up. I can reconstruct those emails. There's some chat connections. Just some FTP connections. Okay, so I found my...
As they say, Big Brother is watching.
Yeah.
So there's someone who went to the site. I'm just going to show as a proof of concept what reconstruction can do. There's some very powerful security use cases to show and ask you what something like this can find. But what this is doing is it's stitching together all the images.
Can you tell me what credit card he just used?
It could, depending on the channel that was used. So it's basically reconstructing the web page, and it's still fetching. This is a slow link, I guess, so to the server. So it's, but it's stitched together the web page from raw packets. It correlates different connections, you know, and it can do this for a large number of applications. And if you have keys, then it can reconstruct even encrypted, you know, email communication within your company, for example. So, but there are some. But this is more of a, I don't know, more of a demo mode than anything else. There are some really specific use cases for reconstructing things and asking you things you cannot see otherwise, which will not show up on a web page, but are there behind the scenes, like cross-site scripting attacks. If you want to see JavaScript, if you have SQL injections, you want to see the URL. The other thing which is interesting here is the big thing actually is a metadata-based bird's eye view. I have a bird's eye view of all my interesting security metadata. I've defined certain user-defined alerts. I have other types of content. You know, attachments, email from. So browsing this is a lot more user-friendly because we've done the effort of going to each protocol and extracting whatever is important and showing that in a bird's eye view. Now I can drill down on it, switch over, do a detailed forensics, all that. I don't know if I'll have enough time to go into other stuff. So there's, we can probably just do a Q&A.
I think this is a good opportunity to go back to your concluding slide with your contact information and have people approach you directly for doing online demos where you have more time. I think the key thing here for this session is to understand that cybersecurity is not some monolith that you just take one device and it solves your problem. What we saw today from the presentation by Shivank is that it's a complex process. It involves some hygiene type things that you have to do in an organization, clean up your act, create very well defined roles and responsibilities, put the appropriate tools, don't trust them too much, constantly be on the lookout to identify new vulnerabilities and figure out ways of mitigating the risk. It's an ongoing process, and that's why I call it more of an art than a science. It involves many sciences, but it's really an art, like an artist, the way they put a painting on a canvas. An architect of cybersecurity has to look at it in that multidimensional way. And then the other thing is that we should not be hopeless about it. Human being, the ability to be innovative is there. And through colleges and universities and national labs and then getting into the private sector, amazing ideas are coming out and getting commercialized, which is trying to make some sense of this complex problem. Because if we don't take the best of science and technology and process and learning and put it in to smart grid, then all the benefits that we're talking about smart grid, whether it's demand response or electric vehicles or monitoring the grid, if we become more vulnerable to attacks leading to lower availability, then what was the benefit? So this is why it's important for us to remain at the cutting edge, and we have to remain informed and try to see how we can take these innovative ideas that are coming out of the academia, national labs, and commercialize them. We can't just say, oh, it's good enough because we have TLS, or we are good enough because we have so many bit encryption. People will attack systems and use encryption, just as we were talking, that encryption can be used as a device to protect an attack, where a tool that's monitoring every packet is not able to see in real time what's happening. So we cannot be naive about this. And that's what the purpose of this educational series is, and what specifically this presentation was to show the complexity first, but then telling you don't get overwhelmed by it. There is a way to solve this problem. It's methodical, and there is a beginning, there is a middle, but there's no end. You just have to continually innovate to address these threats. So at this point, what I'd like to do is go back online, and you would think if there are any final questions, I'm going to ask the folks online if they have any final questions, and then we'll talk a little bit about our next couple of events, and then we'll close. So are there any questions online?
I thought you were going to put up the reference.
The reference page?
Slide 22, I think.
Somebody asked.
So we can go up a few pages. Is that it?
Yeah. The blue's so hard to read.
Oh yeah, it's very light.
Yeah, but when you
we
send that to us,
we will send it.
Yeah.
I'm good, thank you.
So I have one question.
Yeah, go ahead.
I think what you Tony talked about how you'd monitor a network and find its vulnerabilities, but I believe it all starts with architecting the right network. In your view, having looked at the vulnerabilities of every network, is there an ideal network where you can't monitor, therefore no one can? How would you go about designing something that does you out of the job? That's a question for you.
Maybe something for me to think about. But I think the real answer is security is just about setting the bar, and there's really nothing like perfect security. And the whole idea behind putting a device like this or any other device is just to up the bar. To prevent it, you can minimize it, but I don't think you can prevent it. To be honest, because yes, you can do a lot of you can have a lot of encrypted infrastructure to prevent snooping in what's happening or prevent man-in-the-middle attacks. But there are so many other forms around that, and they keep emerging on a day-to-day basis that you sort of need to have complementary systems to help you with the process. So I honestly, there is no answer for a perfect security model right now. It's just that about upping the bar.
I have a question. So far, I understand that the drone is a network well exposed. But how did the CIA keep their secret network? Because the spies need to talk to spies, right? They have to talk over some kind of a secret network that we don't normally know. How could they keep that secure?
So there are obviously there are high level of they use encrypted channels,
okay.
And they use sophisticated ciphers and really hard to break encryptions.
Okay.
All kinds of asymmetric keys and all the fancy things you can imagine to protect the infrastructure. So it's the highest level of security that we know of today.
I see.
And it's difficult to snoop in. You can't just snoop into that traffic. But you can look at patterns, and you can determine from patterns what's happening to some extent. But you can't monitor the data when you have that level of security. Yeah. But when you have quantum computers tomorrow, then watch out.
No. Yeah.
So a couple of things. One is the propaganda is of it being a lot more secure than the reality.
That's true, actually. There's always a backdoor. If you work hard enough, what we found is pen testers can break into literally any network, the most secure networks. There is a way. May not be through that encrypted channel, but there are workarounds.
Then the other thing is that give control to the fewest number of people and watch them like a hawk.
Okay.
And have layers and layers of people observing other people. And that's what leads to a lot of the overhead in large projects like intelligence. So there's that redundancy element. And then the other thing is that the systems are very dedicated. In other words, a lot of the vulnerabilities that we face are from networking. Why do we network? So that lots of people can talk to each other and have access to each other. They don't go with that mindset. It's like the fewest number of people to get the job done. Isolate the systems as much as possible, whitelist applications, check everything. You can't stick a memory stick anywhere. You know, there are processes that are there to protect. But even then, they get compromised all the time. But even that is classified on how often they get compromised because they can't tell you. So it's not as evolved a science as one would like to think.
Because the traditional argument is always, I mean, I had a pair of the RS-232 lines going between, and I was really secure. Why the hell I want to go IP? I mean, really. But on the other hand, we all know that if you don't go IP, you'll be RIP.
Wonderful. So any other questions in the audience here in the room? Go ahead.
Just a quick question on, I know that you guys have been around for a while, and how much of the business was done for the utilities versus banks and financial institutions?
So the question is being asked about the pie chart of NIKSUN in terms of how much business they're doing in the various verticals. So Shivank? Or maybe that might be a question for Mike.
So,
whatever you can share.
I don't know what can be shared, but
it's hard to disclose. I'd say we have a fairly large percentage of the business that goes to the government sector and the financial sector. We're also adapting our systems and bringing them a smaller scale for smart grid and for the utilities. And we found lots of homes there. So this is a very interesting segment as smart grid gets to begin to deploy, where I think we can add a lot of value.
So the point that Mike, who is the salesperson here from NIKSUN, knows about where the technology is going, mentioned government and financial services as being like key customers, but they're finding a niche market in the electric sector with maybe some smaller scale devices that can be put strategically across the infrastructure.
We have ruggedized devices, for example, that have solid state memory rather than disk. They're smaller, but they're very rugged, so they can go in remote locations and do the data collection there and still run the same software that would aggregate up. So these are some of the developments that are happening.
And there's mention about ruggedized devices, and we will allow for direct exchange of information to occur because it's important for all of you to get the information about the specific vendor and their capability, but to keep the focus of this as an educational series, I think that there's some really good lessons learned from this presentation today. I, for one, am very hopeful that if there are products and solutions like this in the market, at least we have a fighting chance. It is still work in progress, and they probably have a roadmap, and they're adding more bells and whistles. But the key thing is to be able to take data and be able to dance with it. And when I say dance with it, I mean pick it up and see it in its layers and its interrelationships and be able to get forensic information out of it to resolve anomalous behavior. And by the way, not all the information that a product like this will capture have to do with intentional attacks. Even system errors, even things that are caused by natural disasters, that could hit multiple sites. At least there's some way a pattern can be recognized and then the appropriate mitigations can occur. So don't think that this is just Sherlock Holmes looking for the malicious hacker. Okay, some concluding remarks. One is that our Smart Grid educational series has now completed a full calendar year. Today, we finished 12 months where we are having seminars and webinars as a free public service. This is my gift to the United States and to all the countries in the world. There are about 10 countries now who have people who sit on these calls. Because I feel that this is the way we can cross that threshold where the innovation and creativity of individuals who had a price barrier to knowing stuff. That is no longer there. We're sharing this information free of charge so that you can come in and be creative in this industry. And then if you ask me how to do something, then we can talk shop. But for the sharing of information, we want to keep it free. Our next event is going to occur on January the 8th. It'll be a Tuesday. And the following event in January will be January 23rd. And the January 23rd will be a seminar and a webinar, and it'll be hosted right here at IBM. And Mike Borton, who's sitting to my left from Grid to Home, is going to be presenting on the Smart Energy Profile 2.0, kind of give us a status update, and maybe talk a little bit about the products and services that he's creating at Grid to Home to commercialize Smart Energy Profile 2.0. So we're really excited and looking forward to that. The January 8th one is not finalized yet. I'm still in negotiation, and as soon as I will know, I will share the information. I hope for it to be a big surprise for the industry. So I am going to now, at this point, thank everyone online as well as in the room, and I will stop the recording, and the presentation will be put on a Dropbox and will be shared just like the webcast recording, and you will be getting that in the next few days. And with that, have a good night. Thank you.
Thank you.